In this video, we're going to be going over how to modify the single cycle data path to accommodate the branch not equal instruction. So let's get started. The first thing we're going to do is create the functional form of this instruction. Basically, the instruction looks at two registers, in this case T1 and T0, and it tries to determine if they're not equal. If they're not equal, it goes ahead and branches to a label. So let's write that out. If T1 and T0 are not equal, which means that the 0 bit is equal to false, which is 0, then I want to branch. In order to branch, I need to take PC plus 4 plus the immediate. And the immediate's not quite good to go. I need to left shift that by 2, which effectively multiplies it by 4. And I need to put that into PC. So that way the next time PC is read, it will go to this address. So now that I have the functional form, I can go ahead and start trying to draw out the path that it's going to take. I'm going to need both the control signals and the path. Of course, the path is dependent on the control signals. I like to figure out the path first when I have unique opcode because I don't know what the control signals are going to be. So trace that through. I know that this is register RS, this is register RT, this is register RD. They're easy to remember because they spell out STD. RS is going to go ahead and flow right down into the ALU. RT is going to do the same thing right through this MUX. We'll figure out the control signal for that later. The ALU is going to perform a subtraction, and I don't really care what the result of that is. All I care about is whether or not this 0 bit or 0 flag gets raised. So I need to modify this signal up here because this MUX either selects PC plus 4, PC flows up from here, gets 4 added to it, or it selects the new address. The new address comes from bit 0 to 15. It's a 16-bit immediate. It gets sign extended. It gets shifted left. And then it gets added to PC plus 4, and we select that. So basically, we're just deciding, do we want to select the branch address, or do we want to select the next instruction? So we are going to have to add in some new hardware to do that. Logic is basically going to be the same. We can add another AND gate. And it's almost the same as branch, but we'll need a new control signal to do this because we have a unique opcode. We're allowed to do that. So I'm going to add a branch not equal signal. And I'm also going to take the 0-bit signal and bring it over to this gate, but I'm going to invert it. It's an inverter because I want this signal to be 1 when the 0 flag is 0. So when the 0 flag is 0, it means the result is not 0. It's a little bit confusing because it's slightly backwards. So now, if I didn't need to worry about whether or not the branch functionality still worked, I could just route this straight into the MUX and I would be done. But unfortunately, I have to branch if either the branch not equal instruction is being used, or if the branch instruction is being used, or being the operative word there. So I need to make an OR gate. Put that over here. And I want to branch if either of these signals are true. So if this becomes 1 or this becomes 1, we're going to branch. And I'll use that to make my decision. And I can go ahead and erase this right here. So at that point, we have all the hardware that we need. So let's trace it through and see if this works. So RS and RT flow into the ALU, and a subtraction is performed. If the result is 0, then the 0 bit becomes 1, it gets inverted here, becomes 0, it doesn't branch. If the 0 bit is 0, meaning the result is not equal, or T1 and T0 are not equal, then this becomes 0, goes here, becomes 1, branch not equal instructions enabled, so that's 1. So we have 1, 1 going in, 1 and 1 going into the AND gate, that puts out 1 of course, and obviously the OR gate will put out 1 because at least one of its inputs is 1. And that'll select 1 here. Just like earlier, it'll take the instruction, sign extend it, left shift it by 2, and add it to the current PC, giving us the branch address. So we can trace that in if we want. come up through here, go into here, go to there, and then go back all the way around to PC. So at that point we're done. We know exactly how everything's going to flow. Now we can add in our control signals, and the control signals are pretty easy at this point because we know what everything has to do. So we can just kind of trace them down. Reg des goes down to this mux down here. That's for writing a register. We're not writing any registers here, so I don't really care what it is. Branch, that goes over to this AND gate. We want the AND gate to always be 0 because we don't want it branching. The branch is for branch equal, and this is branch not equal. So we want to make sure that that's 0 so we're not branching equal, otherwise it would be the opposite of logic we're trying to do. Mem to read, or mem read, that one we really don't care. There might be a little argument about this. The reason I say we don't care is because even if we're reading from the memory, the ALU is going to be putting out all sorts of results, so it's going to be reading all sorts of registers. But that read data is just going to go to this mux, and it's going to flow down here to the write data. We're not going to enable write on the registers, so it's relatively harmless. It'd probably be better to have it 0, but it's not going to change anything. So I'm going to leave it as a don't care. Mem to reg, that one we also don't care since we're not reading anything from the memory. We don't care if we take the ALU results or the mem results. Either way, it's fine. ALU opcode, there's 3 choices for that. It can be 0, 0, 0, 1, or 1, 0. Those are add, subtract, and function. We want to subtract because we're trying to see if they're equal, so that's going to be 0, 1. Mem write, that one has to be 0 because we definitely don't want to write to the memory, otherwise we might corrupt some data. ALU source, that one has to be 0 as well because we want to make sure we select RT. And reg write also has to be 0. We don't want to go writing to the registers willy-nilly. So after that, we're pretty much done. We have our control signals. We know how the data path is going to flow. We have our functional form. And I think we are good to go.